So graphs of derivatives is what we were going through already. Just a reminder, because you might need to recap this in order to understand what we're doing now, this lesson. So if the derivative of a graph is 0, the first derivative, so first derivative tests, if your first derivative equals 0, this means that the point is either a minimum, a maximum, or a point of inflection. If the second derivative is 0, this means that it was a point of inflection, so f dash dash x equals 0, that's a POI. If the second derivative is positive, then it means it was a minimum, positive smiley. So if the second derivative turns out to be positive, it's when you sub in x, then it was a minimum, smiling. If the second derivative turns out to be negative, less than 0, then that means it was a maximum, it was frowning. That's more the second derivative test. So if the derivative is positive, if the first derivative is positive, this tells us, of course, that the gradient is positive, which meant the function was increasing because it was going upwards. If the first derivative turns out to be negative, this tells us, of course, that the gradient is negative, so the function would be decreasing, going downwards. That was a little summary of things that we can work out. So you guys, we were practicing like how the notation. So write down the intervals for whether increasing or decreasing. We're practicing using like domain and range style notation, but specifically only talk about the x when they want to know the intervals. Don't talk about its y. They just talk about the x's. So all the increasing ones were here, decreasing ones were here. Of course, it doesn't have the equal to sign on it because at those points they're maximums or minimums. They're neither decreasing or increasing at these points because they're gradient 0. So that's why we don't have the equal to sign on there. Okay, so you did some practice. So you practice finding the derivative. So we have 3 functions, and these 3 functions, they're kind of our original functions for the next few pages. So these 3 functions, what did we use, Calvina, to find the derivative of this one?
We used the 3 and a -2.
Yeah, exactly. Just regular calculus, isn't it? Yeah. Did we use anything fancy to do the derivative of the red one? Yeah, it's regular calculus. Did we use anything fancy to find the derivative of the blue one? Yeah. Quotient rule, good, yeah. Yeah, very good, because the product, it's a rational function, so it's expressed as a fraction where the top is a function and the bottom is a function. So we used a quotient rule, which you guys remembered as u dash v minus v dash u over v squared. So we worked out what u is, wrote down what v is, and then what u dash is and what v dash is. Sub them all in. And then notice you can remember with the quotient rule, you can leave the bottom like v squared. You don't need to expand it. They're fine in the textbook and exams if you just leave the bottom as v squared. Whereas the top, they want you to expand and simplify the numerator. So you can leave the denominator as is. So this was our first derivative, first derivative, first derivative. Yay. And then down below, you're asked to use these first derivatives, this is what we're up to now, to state over which intervals the function is increasing or decreasing. So use the first derivative to find any maximums or minimums, because at the first derivative, a maximum, the gradient is 0 for a maximum, minimum, or point of inflection. So I've got etc. So the first function, remember, was y equals 2x cubed, negative 2x cubed. Its first derivative, you guys found it to be negative 6x squared. So what we do is we set the derivative equal to 0, because at a maximum or a minimum or a POI, point of inflection, the derivative is 0. So we sub in 0 for the derivative, solve for x. We found, okay, at x is 0. And then what we did was, notice this is not a graph of g of x, this is a graph of the gradient. So here we've just graphed the gradient function. And remember, it's at x equals 0, we have a turning point. And it would be at 0, 0, because remember, like transformations of functions, there's no like +7 at the end or no x minus 3 in brackets. So its turning point, its vertex is just at 0, 0 for this kind of function. And it's negative 6x squared, the gradient function, so it's frowning. So 0, 0, and just did a basic sketch of it. And you're asked to state over which intervals each function is increasing or decreasing. So let's see, we've got increasing from negative infinity. Oh, hang on. No, it's decreasing the whole way, isn't it? No, we're right. Hang on, just one sec. So this particular one, increasing from negative infinity to 0. decreasing from 0 to positive infinity. Does that make sense? So looking at the original function.
I understand what we did yesterday, but I'm just hoping there's more examples I will understand.
Oh yeah, exactly. This is confusing stuff. Now, have I done that right? So the granny is always a negative. Okay. I think I've just done a boo-boo there. What's that? Sorry?
How come when you read B, you just thought, like, what indicated in the question that you have to find maximums and minimums or POI?
Right. So the maximums and the minimums and points of inflections are like the boundaries between where they change from increasing to decreasing.
Okay.
Yeah. So for us to know where something, like say on the previous page, for us to decide where these functions were increasing and decreasing, we use their maximums and minimums as a boundary. Because here at this one, it's increasing, and then suddenly, bang, it's decreasing. And here it's decreasing. And the point of inflection is kind of like it increases from here to here, and then it hits 0, and then it increases here. So the maximums, minimums, and points of inflection, they're kind of like the boundaries for where it stops increasing or decreasing suddenly. So that's why we need those. I think I just did a boo-boo on this one. Because what I was talking about, here by mistake, I might have made a boo-boo here, but that's fine. We'll just go over it again. Because what I just have written is where was the gradient function increasing and then decreasing. But I wanted to know state over which intervals the original function is increasing or decreasing. So I'll show you what I mean by that and why I'm wrong. It's just the part in yellow that's wrong, so we can fix that up. So I'll just quickly, let's clear this. So what was the original function? What was the original green function? Good, yeah, let's do that, and I'll show you kind of what it should be more so like. Negative 2 x cubed to the power of 3. Let's graph it. So I'm just graphing the original function now. Negative 2 x cubed. So what kind of graph, does this have a maximum or a minimum in it?
As a POI.
Yeah, it's got a point of inflection, doesn't it? So I just realized, I by accident, down here, gave a very detailed description of where the gradient function's increasing or decreasing. I just forgot momentarily that it's asking where is the original function increasing or decreasing. So this one, notice it's constantly decreasing to here until it hits a point of inflection at 0, and then it continues to decrease. So sorry, I've got to fix that. So it's actually decreasing for both. It's decreasing for both. Sorry? Yeah. So all you have to do is change this to decreasing. But what was your question, Grace? Yeah, exactly. Yeah. So, and that's why it does make sense, because see, the derivative is always down in the negatives, isn't it? Because the y-axis here is the derivative. The derivative's always in the negative.
Why do we use the derivative?
We just use the derivative because the question said use the first derivative too.
Shouldn't we graph a function?
That's what she just did, isn't it? Oh, you mean instead of variables?
You could graph it, but you could also graph the first, like this also proves that it's decreasing. This proves, because see, the first derivative is always negative. So that's why, and if the first derivative is always negative, except for here, because that's where the point of inflection would be, then it's decreasing. If you want, so yeah, you could have drawn this is a graph of the derivative. You could, if you want, do a quick sketch of the original function as well. So I'll just need to change this. We need to change this because it's actually decreasing over both. Because it's negative here and it's negative there. But because see the original one, it's decreasing, hits 0, and then it decreases again. So it might be a good idea, like Talise suggested. You can leave that one there, that's fine. Do we graph it? Because it's good to practice graphing the derivative as well, because sometimes they do ask you to graph the derivative. But we can also put in a graph of the original function. So it's actually decreasing over both. So it's decreasing.
So what's the point of using the first derivative?
Just the question stated, use the first
Like it
derivative.
doesn't help us at all.
It helped us to work out where does it stop decreasing momentarily. So that's what that was for, just to work out. Yeah, so you're right, like what was the whole point of using the first derivative? It was purely to find out where is the boundary where it suddenly stopped decreasing. It decreased and then it hit x equals 0.
So it's a point of inflection?
Yeah, it's a point of inflection, yeah. And this gradient function proved to us, to see the gradient's always down in the negative y's. So it proved to us that the gradient is always negative either side of that point of inflection. So that's just the whole point of that part there, the graph. When we graph the great derivative, it proves that it's negative. So it's just because it said use the first derivative, so that's why I graphed it. You didn't have to, no. You probably could have. But this kind of helped maybe to demonstrate. Like we don't know, like here at this point, all we know is, using the first derivative, all we know is that 0, at x is 0 was where the point of inflection was. We didn't know if the graph was always going up like positive or was it negative. So by graphing the derivative, because it ended up in the negative y values, meant that that proved to us that it's a downwards one. It's a snake going back into the toilet. It's confusing, hey?
Yeah, it's confusing.
It is confusing, yeah.
The next example, the
Yeah.
next example, probably more
So
complicated.
what do we draw to actually answer the question?
Because the question said use the first derivative,
Well, that's just the gradient.
use the graph of the first derivative. It proved that the original graph was going down instead, because see the derivative's negative. If it was one where the snake's coming out of the toilet, it would have been up here. The derivatives would be all positive.
Right, but
Yeah.
they should have to graph the gradient.
Yeah, this is
Derivative is
the derivative. Yeah, see that's g dash x. This is not the original function. This is the gradient function. This is the graph of the first derivative.
So what do you mean when you say gradient function?
The first derivative.
Pressure is equal to
Because every time you're saying gradient function, I'd be thinking like,
Yeah, they are the same thing. You're right. It's good to clarify that. Gradient function is the first derivative. Yep.
let me write that down.
Yeah, that's a good thing to write down. The gradient function is the first derivative. If you've got any space, you might want to make a note that that's a graph of the first derivative. We could have just, if they didn't say use the first derivative, we could have just graphed the original function. That would be fine. So notice, so Grace was asking, why am I using the first derivative? If they didn't ask us to use the first derivative, I would have just gone ahead and graphed the original function like we did here and work it out that way. But the fact that it said use the first derivative meant I used the first derivative, set it equal to 0, solved, and then used the fact that the first derivative's negative, so it's all down in the negative section, which meant it's going down, it's decreasing. Whereas if it was up here, if it was positive 6x squared, the graph would have been going up like that instead. So confusing, yeah. Just the fact it said use the first derivative. Okay, so the next one, remember the original function for the one, we're doing the red one now. Oh, yes, Katie? Yeah, sure. Yep. We're doing the red one now. So there's the original function.
So that's the answer for the green one.
Yeah, the answer for the green one. So you can maybe section this one off. So what we can do is, if it makes life easier, calibrate it today. Yes, you are.
Well, that should come here.
Let's section that bit off. That was the green one. Now we're about to do with the red one. So the red one, it's a cubic function as well. So the green one was a cubic function originally. The red one's a cubic function again too. Its derivative, because it's a cubic function, its derivative will be a what kind of function?
Quadratic.
Quadratic, yeah. So you already found what the function was. You can write that again. F dash x was 12x squared plus 24x.
So because it's subtract, I thought it was subtracted.
Oh, was it? Yeah, it was, sorry. I'll undo that.
So because it's subtracted, it's
That does make a difference.
the coordinates is not going to be 0, 0.
Yeah, the coordinates are not going to be 0, 0 for this one. Yep.
You're such a bad genius.
Yeah, I thought it would have got more recognition for that. Like, that's really quick, but it's thanks.
Huh?
I have a question about the last one.
Yeah, sure. Yeah.
Because they're both decreasing, could you technically do like negative infinity is less than x?
So
Is
snake
less
is
than infinity, less than infinity?
you could, except at the point of inflection, it's not decreasing momentarily. It's 0. It hits 0 then. Yeah, for it to be decreasing, then the gradient has to be negative.
That, and then you wrote
So negative gradient,
I
negative
saw the
gradient.
negative.
But at the POI, the gradient's exactly 0, so it's neither negative or positive at that point momentarily. That's a good question though. Yes, Lauren. All right. Promise me come back. Okay. So. Okay.
Gracie, that's how you done this lesson.
But it's just really cringe because I have to out.
Yes. Okay, so it's uncalibrated again. So f dash x. Oh, and what is f dash x? Can you tell me what to write?
That's 12x squared.
Yep, thank you.
Plus 4x.
Plus what, sorry?
24x.
Thank you, 24x, yeah.
Minus 30.
Minus 36, yeah. So I by accident had plus 36 before. So this is a red one. Guys, this is hard stuff, so concentrate. I know you've been patiently waiting for me to calibrate. So what we do is the first derivative test. We need to find out where any maximums or minimums or points of inflection are first. And to do that, set the gradient equal to 0. Well done. So now let's set this equal to 0. So 0 equals 12x squared plus 24x minus 36. This is a great one for practicing factorizing quadratics.
Ooh, I think we should 12, take 12 out.
Yeah, good. Take 12 out as a common factor. 0 equals 12.
X squared.
Yep.
2x. What is the
Yep. Minus 3, good. And then what do we do next to factorize? Come here. What do we do next to factorize a quadratic?
Honestly, I don't know.
Factorize a quadratic?
Yo.
You make a whole
Like a yes.
Oh, wait, what?
I know.
So what adds to 2 and multiplies to negative 3?
Yeah.
What?
Negative 2 and negative 1.
Close?
What did you do? Negative.
I have
Please
to
factorize the quadratic.
Negative 3 is negative 1.
Negative 3 and 1.
No.
Negative 3 and negative 1.
Remember quadratics? Factorizing?
Yeah, I know that. That's confident you said make it equal to 0.
Well, because
That's essentially what you're doing, but I wouldn't have worried like that if you just like really threw me off.
yeah, blame it all on me. Why don't you?
Okay, so what are our two values of x?
You just laugh at anything I say.
What is it?
1.
Yeah, 1 and?
1 and 3.
Yeah, negative 3, yeah.
I was really struggling to figure out
Yeah,
what plus 3.
x equals negative 3, x equals 1. So now, because it says use the first derivative, we're going to graph the first derivative. It's a good thing to practice graphing anyway. The first derivative.
What was that?
First derivative, yeah. Is that x?
I'm doing it.
Is that y? What are our two x-intercepts for the first derivative?
Negative 3.
Good, negative 3 and 1. Notice we're graphing f dash x. I don't know why I wrote y. It's actually f dash x.
Tengo demasiados deberes para hacer.
No more negative. Focus on that language.
You know what I just said, Paige?
So guys, okay, this is f dash x we're graphing. What are the two y-intercepts? You said it before, sorry.
Negative 3 and 1.
But negative 3 and 1, so let's graph that.
Isn't
Negative
it
3.
x-intercept?
Yeah, they're x because we're graphing the gradient.
But you just said y-intercept.
Did I say? What would be the y-intercept out of interest? Of the
You don't
gradient?
know.
Yeah, negative 36. Remember the
I'm
y? Yeah, the c is the y-intercept, yeah. Negative 36. So it's going to be kind of like
Quadratic.
this style thing. So crotch is at negative 36. I might mark in 1 and negative 3 just there. It's negative 36 down there.
Very small scale.
Raise to 70. You drew a 6. Imagine having a zone.
Yeah, we need to know where the vertex is. Oh, actually, no, that's a very good point. I keep by accident keep getting mistaken and thinking this is the original. It's not the original. This is the gradient. So where is the gradient? So where it's above, where the gradient functions above the x-axis is where the original one would have been positive. And where it's below the x-axis is where the original function would have been decreasing.
So where it is where the original function is.
Yeah.
I would just say decreasing and increasing.
That's
Increasing. The original function would have been increasing from negative infinity to 3, negative 3.
What?
and from 1 to positive infinity, because it's got a positive gradient. See the gradient
Oh,
above?
so if it's a happy face, increases time.
Yeah, like this function, the original function is like one of those roller coaster ones. You know, roller coasters where it's got an increasing bit, an increasing bit, a decreasing bit, or a decreasing bit, a decreasing, and an increasing bit.
So basically, we don't need to draw the little parabola. We can just use. Oh, that's a lie. We can just use the points, and then once it hits it, it goes up a bit, and then it changes.
So it's negative
what?
3.
Yeah, so it's positive. It's got a positive one to begin with and a positive one at the end. So it's more like this one. It's positive at the beginning to here, and then it goes negative between here and here, and then it's positive again. You see it's above, the gradient's positive. It's a positive gradient here. It's a negative gradient here, because this is down in the negative y, and this is in the positive y.
So you're saying too many things that's so fast, and it's a
It is
borderline that's
fantastic. This is
confusing.
weird, this stuff. This is weird stuff. What would be the x-coordinate at that point? What would be the x-coordinate?
0.
-3.
Yeah, good, -3. See that it would be here. What would be the x-coordinate of that one? 1, yeah, do the other one. Because here, notice that it's positive gradient. What's that? At the top, because it's a positive gradient, and then suddenly it spins around and becomes a negative gradient, and that's why the gradient's down in the negative. And then it's
Oh!
and it changes to being a
So
positive.
that's the function,
Yeah.
and that just represents the derivative, the gradient.
Yeah, this
So
is just telling us
basically-
if it's positive or is it negative.
So that's why up until -3, it's positive. It's in the positive,
Yeah, positive y's, because that's
positive
the y.
y's,
Yeah.
and then it goes down to the negative y's, so it's going down. Then it goes back into the.
Positive y's, yeah, when it's
So as the
It's weird,
gradient.
though, isn't it?
Oh,
Yeah,
this
positive gradient.
With the gradient.
It's hard to see that at first. It's hard to see that at
So if
first.
the gradient graph is not really directions given, it's just about which coordinates in.
Yeah, it's sort of like that. Which zone? Like this is. These.
Because even though it's going down, it's not negative, it's positive in a positive coordinate. So it doesn't matter direction, it's
Positive
just
up here,
which
yeah.
one they have.
Yeah, these are. Yeah, I see what you mean. You're thinking this like a unit circle. These are in positive y values
Yeah.
above the x-axis. It's in negative below, and this is the boundary between the two.
So next.
It's confusing, hey?
Yeah.
But and it's if it didn't say use the first derivative, we could have just graphed the function and worked it out that way. Worked out it's increasing here, it's decreasing here, it's increasing here.
Oh.
But it's just a question that said use the first derivative, so that's why we used it to get the algebra, and then we graph the first derivative, so that we can prove we've used the first derivative to decide.
So that the function for the green graph.
The green graph, yeah, the gradient
That
one,
is the. So that's the gradient
yeah,
of which.
of that one, of the original one, because the original is a cubic. Original's a cubic. So therefore its gradient function will be a quadratic. Yeah, it makes sense because the original is a cubic, the blue one, so its gradient function would be a quadratic, the next
it's
level
that
down.
The negative positive.
What are you talking about, the blue thing?
Yeah.
The top one?
So this is like the.
If the gradient function out of interest was frowny,
It's the. So
it'd be negative,
positive.
positive, negative, yeah, it'd be more like this one. The original
It'll be a
function.
what?
If it was a frowny, if the gradient
Yeah.
function was frowny instead, notice it starts off negative, and then it goes positive, and then it goes negative again.
Okay,
So,
so
it'd be
this
more
is
like
all
this,
relative to
negative,
y
positive, negative, yeah. And it is confusing, that's why in a way, like I was more than happy to leave this at the end of last year and come back to it, because it is a strange thing, it's a strange concept. So now finally after all that, we need to state over what intervals is the original function, therefore, based on this, over what intervals is it increasing. So it's increasing from here and here, because it's got a positive.
Increases to from where?
Yeah, from negative infinity to -3.
Yeah.
Yep. And also from 1 to positive infinity. So it's increasing over these intervals, that's right there. So from negative
I thought
infinity
it was
to -3.
decreasing there. Just goes
Oh,
down.
but it's got a positive gradient. Positive gradient. Positive gradient because it's in the positive y. If it's down here, it's got a negative
But
gradient.
why are we using the gradient? Because that just makes it difficult. Why don't we
It does.
look at the original?
Exactly. Just because the question says use the first derivative.
This is just.
I see why we're only doing 1.5 pages.
Yes, yeah, because this is conceptually weird. So it's increasing from negative infinity through to -3 when I'm in a space, and also from 1 to positive infinity. To positive infinity. And we also need to state, where is it decreasing? So this function is increasing here and here. It's decreasing from here to here. So let's say decreasing. So notice if it's decreasing, it's got a negative gradient, which means it's down below the x-axis. How would you describe the notation? What notation would you use for the decreasing part?
X is greater than -3 and less than 0.
Less than 1.
Less than 1, yeah. You see from -3 to 1 it's down.
Oh, is that whole
Negative.
thing?
So -3 to 1, yeah.
Oh. I did as 2 separate things instead of just one thing. I don't want
Oh, I just wrote infinity instead of x.
Was I singing that?
Yeah, I think so.
-3.
I think when I go in Canada, it's really going to help with like because jurisdiction.
Who's gonna have order?
So that was just the second one. Now we've got that third awkward one to do. I'm going to have to calibrate again, sorry.
It's chop.
Walk it straight.
Go to dragon yourself instead of him.
Look at the same
No way. How do you look like? I tried it. I tried it and it was the same. It's not.
Yeah, I'll scroll down for you. Yeah. I'm just separating off this bit. So some people are writing all this stuff down and making notes of it, so I'll just let people do that first. So before we do the third one, we've got to do the blue one still. The blue one's a little bit more awkward because it's a more complicated function.
What do we do right now?
Some people are just writing down this middle part, yeah. They're just writing down and taking notes. So it is giving people a moment to write them down.
So, Mr. Lily, I think I'm going to have to come talk to you after school.
I'm going to be in room
I'm
41.
going to be in a class.
So Krista, after school, I'm in room 41 doing math surgery.
That's what?
Math surgery.
What does that mean?
Like, you know, extra math, like when people want to come and get help with homework sheets and stuff like
Friday
that.
afternoon?
Yeah, I do it every day 4 after school, and I've got a student coming in from year 7, so I'm definitely going to be there.
You don't come up to Ivy and say,
I know, they're not allowed to, so I have to be over in room 41.
well, I'm not allowed to come over there.
Mm.
You're going to make me go all the way over there? How about we just chat on email?
They're probably a bit more constructive in person.
So how long are your course?
Until like the student goes, I guess. Like they might not leave until 5 for all
Well,
I
I'm
know.
going to come. If I come, I'm going to have to wait for you to finish with that.
No, they're just going to be working on worksheets and asking me for help when they need it,
Okay.
kind of thing. Okay, so everyone got this, I hope? Cool. So we've just done the first one and the second one. Bella, Owen.
Put my decrease in.
Oh, sorry. You want to check this one?
-3.
There you go. Yeah, it is confusing, isn't it? But it's good practice because remember, like, if the graph was cubic, its gradient function will be a quadratic.
I'm inspired to inspire.
That's good. Well, it was a nice thing. That wasn't bad. It was a nice thing.
Like you never, in other words, I've never seen over like,
Acknowledgement.
or like act or something and say, hey kid.
Okay, guys. So if the gradient function, out of interest, like while some people were writing stuff down, out of interest, if you had a gradient function that look like this,
Like what?
like that? Would it be a
all positive.
All positive.
all positive?
It just keeps going up.
Would it be a maximum, a minimum, or anything?
It would be a minimum.
Close. It'd be a
Point.
point of inflection. Point of inflection. Yeah, yeah.
Except for the zeros, right?
Yeah, it'd be more like that kind of thing. Good. Yeah. Yeah.
Yeah.
And that's why its gradient's always positive. See, its gradient's always positive, except for its period.
No, it's just showing the gradient.
Yeah, this is if the gradient function. Yeah, if this was the gradient function. And notice when it's more like a roller coaster style cubic, like it goes up and then down and then up, or it goes, yeah, then it's going to be more like one that crosses.
What?
Like the gradient function will be crossing over because it goes from negative to positive, then to negative,
Wait.
or positive to negative to positive.
Miss
You just drew lines, a bunch of lines that are
It went black. What do you do?
What?
I'm asking you a question and you just
Oh, sorry.
erase all of the things.
Which one? Which one?
Okay, but if that's my
Shh.
right, but see, you said to me if that's my gradient function.
Yeah, if that was the gradient function.
No.
This one.
No.
That one.
Just that one.
That one back. Yeah.
Give it to me right.
Oh dear.
Why don't you get up and point?
This one. The green one.
Yeah.
That one.
This is the gradient function for this graph.
Oh, this one would be.
That can't be the
There'd be that one.
Okay, that's what's confused. I thought you said this was
good.
the one for this one. I was like, but that doesn't make sense.
Ah, well, good critical analysis. So Calvina just made a really good observation. Calvina realized this one couldn't be the gradient function for this graph. And why? Listen, Bella, please.
Because this right here would be any negative part of
Yeah.
x that acts negative.
So it'd be
Which
ne-
means this would have to be decreasing.
Yeah, decreasing more like this one, isn't it?
Yeah,
Yeah.
like this one.
Oh, well
That's what
observed.
I'm saying, it's
That's
a
good.
Y values.
No.
Why is everything
Why
wrong?
values in there? Just think of it this way. But what's it doing? Like when you have the graph, if it's in a negative part, it's going to decrease because decrease is negative.
But I thought
Just think like
negative
that.
Y part.
Says, what are you
Yeah, it's in the negative y part.
Okay,
Yeah,
okay.
because this is the gradient function, yeah.
Yeah.
So it means that it's decreasing. So
That's
it's
really
negative
good.
y part here, so it's decreasing. Negative y part here, because it's decreasing. Positive y part here, because it's
So
increasing.
that's be down, down. So that's what you're talking about.
Yeah, that one, yeah, exactly. And that's what Calvina noticed. I drew two of these kind. And so she was saying, hang on, that doesn't match that one though. So that's what she noticed.
It's butter.
Basically, it's a girl.
So you were right, in other words.
All right, cool. So back up to this awkward one up here. So this awkward one, the rational function. Do you remember things called asymptotes?
Yes.
So vertical asymptotes are all because who's the only person who can divide by zero?
Chuck Norris.
Chuck Norris. Oh, and Gauss. And probably Gauss too. Yeah, and Gauss. Gauss as well.
That was the same topic.
Gauss. Remember Gauss?
Okay.
Gauss, yeah, Gauss and Chuck Norris are the only ones that can divide by zero.
You're right.
So therefore, remember to find any asymptotes, what do you set the denominator equal to find the equation of the vertical asymptote? Yeah. Yeah, no, oh, close. Set the denominator equal to zero. Because, and remember an asymptote is a ... region where the graph can't exist. So to find the equation of the line where the graph can't exist, you set the denominator equal to zero because that's not allowed in maths. And then this is, so if you set x squared minus 16 equal to zero, how would you factorize and solve for x?
Well, you would do FOIL first.
I'll just show you here. So, x squared minus 16 equals 0. What's something special about that quadratic?
It's a different squares.
Good, yeah. So what would it be?
X plus
4. X minus 4.
So what would be the equations of the two vertical asymptotes then? X equals, yeah,
X
negative
equals
4.
-4 and X equals +4.
So that's just one thing to point out. This blue original function going to have vertical asymptotes at -4 and +4. That's just something you might want to just kind of remember.
You want us to remember what, Mr. Lily?
This original function, the one we had this last awkward one, it just will have vertical asymptotes. So that's going to be useful to know because there's going to be so the asymptotes might form one of the boundaries between where it's decreasing and increasing and stuff.
Did you do the same thing with the x squared minus sign?
Okay, sorry, I can't hear Bella.
Did you do the same thing with x squared minus sign?
Nah, it's just a denominator. Because in math, 0 divided by 1, that's fine. That's just 0. But 1 divided by 0 is not allowed. Only Chuck Norris and
I can do it too.
So that's the asymptote stuff. I don't know how you could make sense of that. But if you want to, that might be something useful to remember. Okay, we're about to do this awkward one. Please really concentrate on this one. This one's much more awkward. The other ones are nice. Yeah, the other ones are nice. So you found the derivative of the blue function. You found the first derivative. You used the quotient rule to find the first derivative. And you got negative 14x over x squared minus 16 all squared. That's the first derivative. So what do we set it equal to find maximums, minimums? 0. So let's do that. Okay. Now let's do that. Let's set it equal to 0. Where is that again? dy dx equals negative 14x x squared minus 16 all squared equals 0. There you go, that's important. So we're using the first derivative to find over which function intervals it's increasing or decreasing.
Isn't it negative 14x squared?
No, it's just the derivative is above, it's like up in the top half. We've done it with the quotient rule. It was just negative 14x.
I don't like how you like to format, like, earlier you was being like, no.
What are you saying?
Yeah, I am.
But in case
Not maintaining format.
you think I don't, oh, I can't remember. Oh yeah, the width is not as good as it
No,
was.
she means because you put 0 in the other stuff.
No, that's not what I meant. Like,
I think I was quite ambitious trying to do 3 things in one page. In hindsight, I probably would have done only 2 at once. Okay, so if negative 14x over x, yeah, we're going to start to solve.
Okay.
We're going to try to solve. It's interesting, isn't it? Yeah. You could times by the denominator. Times both sides by the denominator. Negative 14x. If you times this by x squared minus 16 squared.
that just equals 0.
It does, yeah. Just equals 0, yeah. 0 times, if you multiply by both sides by the denominator, 0 times that's just 0. So what's x going to be?
0.
Yeah.
What, Marley?
What's that? You're not liking that?
That makes no,
Why did it negative 14? It was not been negative 14, it's still 0.
everything was 0. Actually, I think
See, to solve what at the moment we're solving for x, so we multiply both sides by the denominator, and 0 times the denominator. It is, it's unsatisfying. Something as complicated as that comes to something as simple as that. Do you want me to show you what the original function looks like? This might be a good thing to do, and then this might make more sense then as we go. Let's do a quick sketch of the original function. Oh, sure thing. What was the original function? So to do this original function, what's the numerator, Owen, of the original function? X squared?
Sorry, x squared
Minus 9, thank you, yep. And Sarah, what is the denominator of the original function, please?
x squared minus 16.
Thank you. Here's the function, here's the original crazy function. It's a crackers one. It's crackers. Where do you think the asymptotes are, Bella?
Okay, what did you say was pardon?
It's crackers. Where do you think the asymptotes are, Bella?
Negative, whatever that is, and then positive.
And how did we find those exact numbers again?
It's negative 4 and 4.
Yeah, negative 4 and 4, yeah. We said they do not.
This is
Did you use the alpha y equals? Like, did you make a nice fraction? x squared minus 9 over x squared minus 16.
Oh, I did the derivative, that's one.
Oh, you might have, yeah, you maybe graphed the derivative. I was just showing you out of interest, this is a complicated function. And so where should it be increasing? Would you say here is it increasing or decreasing?
Increasing.
Yep. So we know already that one of the increasing intervals will be negative infinity to negative 4. Good. What about, and then this one will be from here till what x value?
0.
0, good, because you just found the maximum 0. And would this be increasing or decreasing after 0?
Increasing.
Yes, so from 0 to
Negative 4.
close?
Negative 4.
4, yeah, 4, good.
Oh, I forgot it's the x, not the y.
Yeah,
That'd be 4.
yeah, exactly. And decreasing from 4 to
Infinity.
infinity, yep. So we know what the answer is going to be now.
Can I use the graph?
Yeah. So this is a
Nothing too complicated, King. Well, that's just like the world stop coming. Everyone stop reading. You just tell complicated, I'm going to have to read it anyway. You haven't gone yet, so.
my,
And hold your breath. Because the word can't go on without you.
Oh, you know that.
Yeah.
so if we were to graph the derivative, there'll be some negative stuff. Oh no, this is positive, so it's going to be above, and then it hits, then it's an asymptote, and then it's kind of like below. No, it's above still, so it's increasing, asymptote, increasing still, so in the positive, and so on. Anyway, this is complicated. So these ones we could easily sketch the gradient functions because they were just quadratic, so they were easy to sketch. This one's awkward to sketch. So what sometimes people do, you might notice in the book, they instead have kind of like a little gradient diagram, f dash x. Oh no, it's g dash x, is it? No, it's
Y
y.
dash X.
Oh yeah, it's dy, yeah, y dash, isn't it? Or dy dx.
dy dx.
Who heard that?
Who was that?
It's like the howl.
Okay, this is going to be hard to do because it's uncalibrated, so I'll do it here.
That's how we're all feeling it though, from.
Alrighty, so sometimes you can do these little gradient diagrams. So rather than draw, like actually sketch the thing, because we could intuitively sketch these quadratics, they were easy to sketch. We can do these things called gradient diagrams. So we've got 0. 0 is an important point. So is negative 4. Yeah, you might have seen these things before, I'm not sure. And then what's the other important point on this graph?
4.
4, yep. So these are kind of like the boundaries between the increasing part. So having seen,
So it's not relative to y value.
yeah, and having a look at what the original function looks like. So Sarah, would you say the gradient to the left of negative 4, is it positive or negative, the gradient? This is the original function. Positive, yeah, because it's going upwards. That's the original one. So you can do these gradient diagrams. So you can just put a plus there to say in this area it's positive.
Y value?
Oh, this is more so, this is the original function. So this is just pointing out that it's increasing, it's a positive gradient, because this is dy dx. Would you say, Katie, from negative 4 to 0, is it increasing or decreasing? Increasing, yeah, so positive still. These are like just these gradient diagrams. Grace, from 0 to 4, is the original function increasing or decreasing? That's this. Decreasing, yeah, it's going down. So negative gradient from 0 to 4.
Good job, Grace.
And Owen, from 4 to positive infinity, is the graph decreasing or increasing? Close? Yeah, decreasing. This is the original function. It's confusing. You're probably thinking of the gradient one.
Well, we should definitely sketch that.
So it's decreasing.
It's decreasing.
Yep. So remember, all it wants us to do is to state over which intervals is it increasing, over which intervals is it decreasing. This might help you to realize that, and then we can just write it as increasing, decreasing, Bizzo. What's that?
How come we don't write out the original function?
How come I don't write out the original?
Yeah, I feel like it would just help a lot.
What do you mean write it out?
I mean, graph it.
You could, and it's just because it said use the first derivative. If it just said find out over which intervals is it increasing, decreasing, I would have totally just graphed the original. Yeah, I would have graphed the original, but here it said use the first derivative, so we had to see in purple is where we use the first derivative. To be honest, when I went to here, I started to use the original function once I got to the gradient diagram. So it is increasing. This is just to help us work out where is it increasing, where is it decreasing. That's what this little diagram does. And now I don't have to think too much, I can just look at here. So it's going to be, so wherever it's positive is where it's increasing. So from negative infinity through to negative 4, it was increasing because the gradient was positive. From negative 4 to 0, 0, increasing. Laura, what's the next first interval where it's decreasing?
Where it's decreasing.
That'd be 0 to 4.
Yeah, 0 to 4.
4.
No, you're right, okay, 0 to 4. And Felix, where the last interval where it's decreasing? Yeah? 4 to infinity, yeah, good. 4 to positive infinity.
And that's my derivative about.
So it's all kind of slightly messy.
Can you scroll down a smidge?
Yes, so
It says that.
oh, gotta say, oh, great.
Says that.
I want to fix up my yellow. Why isn't it by yellow?
None of us seem like real people.
Yes, yes.
Why don't you ever ask me questions?
Oh, no.
Because I know you know the answer.
Yeah, she has
A little bit, yeah, and you do listen pretty well. And so I'm picking on people that are not always, but.
Okay, so why you always complaining?
I try to pick you more now.
You pick with all of us.
Everybody picks an
Poor Owen.
Little face. Oh.